Yeah, so thank you very much for that introduction. And today I'm going to talk about the research that I've done during my PhD about how to create generative models that actually understand the visual world. So let's perhaps start with the state of the art in generative models in 2025. So it might be hard to believe, but today we can generate striking images that are not only of very high quality, but also, and to me, that's part of the things that still amaze me to this day, it's able to generate images that are creative. So the model is able to take here two priors. First, the prior of what an owl looks like, and second, the prior of what cardboard looks like, and combine these two into an image that creates an owl in the consistency of a cardboard. So not only can we generate striking images, we can also generate videos that look like actual cinematic videos, and of course, converse with humans in natural language. So it looks like deep learning has kind of plateaued in the last year or so, and got to the peak of what we thought was possible. So the question is, how did we get here? How come in 2025 we're able to do all these amazing things that we weren't able to do like 10 years ago? So the answer is pretty simple. We didn't do any very sophisticated modifications. We did two things. We increased the models very significantly, and we added a lot of data. This is what we call scaling, right? And it turns out that when you increase the size of the model and add a lot of data, the model is suddenly able to do all these amazing things. Now, the question we might ask is this entire field not really scientific? Is this entire field of deep learning just coming down to data and scale? Can it solve everything? Now, during this talk, we'll see that these models are pretty far from being actual world models that understand the visual world. So these are three examples of models that we're going to see. These are the same models that we saw, those amazing models in the previous slide, but we'll see that they struggle to understand very basic things about the visual world, right? This is, for example, OpenAI Sora, who claimed to be a physics simulator, right? This is probably the furthest thing from a real-world physics simulation, hands and legs popping up from different places. So my research is basically first about doing an analysis, understanding why the model behaves the way that it does. How come the same model that created an owl made of cardboard cannot generate simple conjunctions? How come a video model that generates cinematic shots cannot understand physics and motion? And then once we have that strong understanding of how the model operates and why it does what it does, we can create a fix, a solution that is not based on scaling. So I'll give you kind of a teaser or a spoiler alert for this lecture. We won't see any additional data. We won't see any increase to the model. Actually, in two of the cases, we'll see that we decrease the model size very significantly or decrease the amount of data very significantly, but still improve the results very significantly based on our understanding of the model. So our goal will be to decipher these models. Now, during this talk, I will only be able to include a handful of works that I did. Obviously, we only have 60 minutes. But I did want to show you kind of a timeline of my PhD and what interests me. So I started off working on interpretability, which is basically our ability to explain the predictions. For example, here, if the model predicts a golf ball, we output a heat map that shows us where the model looked on the paw of the teddy bear. So these two works were published at CVPR and ICCV and have received great adoption from the community and are still to this day kind of the go-to tools to explain transformers. Around 2022, I started to do things that are similar to the things that we're going to see today. Once we have an explanation, can we use that explanation to improve the model? So I did it for both discriminative models, where we actually fine-tune the explanation, and for generative models at the time, GANs were the state of the art. Today, we won't talk about GANs. And then moving on to the last 2 years, which is also the era that I'm going to focus on, the diffusion model revolution, where diffusion models replaced GANs. And I did one work at iClear doing interpretability for diffusion models. For example, here, the model generates this image of a camel, and we were able to decompose it into kind of structure and semantic part. So we can see that the model uses cashmere to add the texture on the models, on the camel's skin. So as I said, just an overview of what I've done so far. But let's deep dive into the first work that I'm going to talk to you about. It's called Attend and Excite. So as we said, around 2022, 2023, diffusion models start to replace GANs. And then a model called Stable Diffusion is finally open source. And the first thing I tried was kind of like, okay, let's test this model, let's see what it can do, right? It's the same model that can generate an owl made of cardboard. But what if I ask it for a conjunction, a photo of a cat and a dog? So very surprisingly, the same model that was able to give us phenomenal visual results that were super creative, right? Inventive, is not able to generate simple conjunctions. So I get either 2 cats or 2 dogs. So why does this happen? Is this really an expressivity issue where the model cannot generate simple conjunctions of cats and dogs? The same model could generate an owl made of cardboard, right? Why does this happen? So as I said, the first step would be understanding the model, how the model works. So let's understand diffusion models. As I said before, diffusion models, GANs were the state of the art. GANs or VAEs. And basically, every generative model in the computer vision realm takes a pure random noise, epsilon, and turns it into a data point, x0, okay? So GANs and VAEs did that directly, mapping a noise to a clean signal. Diffusion models do that process gradually, which I think is much more intuitive, okay? So we break down this process into several sub-processes. And you can see that at each time step, the model adds more details or more features to the image. It also does that in a way that we call coarse to fine. So first we add the coarse features, the layout, and gradually we add finer features, okay? Here you can see the loss that is employed by the diffusion model. We take the clean image x0, we noise the image up to a random time step, and the model needs to predict the noise that was added. Now, predicting the noise is essentially equivalent to predicting the signal, right? If I have the noise, I can remove the noise from the signal and get the clean signal. Now, where does text even come into this whole architecture that we discussed, right? It doesn't look like we can control things with text. So text is introduced through these orange connections here, called cross-attention connections, these KV connections. So now we understand, if we want to understand, for example, why the model generates a lion but not a crown for the prompt a lion with a crown, I probably should look at these cross-attention connections, right? Because they are the entry point of text into the model. So now we understood where in the model we should look, okay? Now let's understand what cross-attention actually does. We'll talk about 2 entities, the queries and the keys. Now the queries are a mapping of the input image, ZT, right? We have a noisy latent in the diffusion process. So what we do is we split ZT into even-sized patches. You see patch 1, patch 2, and so on. Now Q is a vector of vectors, or in the common language, a matrix. The first row of Q corresponds to the first patch, the second row of Q to the second patch, and so on. Now K does the same thing with the text embedding. So the first row of K corresponds to the word A, the second to lion, and so on. Now what cross-attention does is it creates similarity scores. Basically, the first row here of the attention matrix is going to correspond to the first patch. So what we're going to do is we're going to do an inner multiplication between the representation of the first patch and the representation of each of the text tokens. So the score here will correspond to the similarity between the first patch and the word up. The second score here will correspond to the similarity between the first patch and lion, and so on. Okay, but this only gives us scalars, right? So we use softmax to turn these into probabilities. And then each one of these rows defines a distribution over the tokens. Which tokens are similar to the patch and which are not? Questions so far? No questions. Okay, great. So now, instead of looking at this in the row dimension, let's look at the columns. Each column here corresponds to a token, right? A word. And then we have activations for that word across all the image. So we can take that column and reshape it to the spatial shape of the image. And then we get activations for that token throughout the entire image. You can see that this activation actually shows us where the model generates each one of the tokens. So for A, none of the spatial tokens is similar to the token A. And indeed, nothing is generated that looks like A, right? But for lion, we can see that the activations actually correspond to the places in the image where the model generates the lion. Okay? So this actually gives us a spatial signal from the model's inner representation. Now we can easily understand why the model did not generate the word crown. If we look at the activations for crown, the model actually decided that none of the tokens in the image will be similar to crown. So it basically decided to ignore crown, right? As we said, the cross-attention connections are the only place where text meets image. So once the model misses crown at this point, it has no way to understand crown in later parts of the model.
The sum makes sums to one over the rows or over the...
On the rows, yeah, the rows sum to one. This is why you can have small activations here throughout, right? So each one of these sums to one in a different row. Other questions? Okay, so this was part one, right? Understanding why the model malfunctions. But now let's understand how we can use this understanding to actually fix the model or fix the model's behavior. So let's look at our nouns in the sentence, okay? Crown and lion. And let's kind of convert our intuition into math. So let's look at the maximally activated patch for each one of these tokens. And let's define the loss to be exactly our intuition. What's our intuition? A token is generated when it has high activation somewhere in the image, right? So let's convert this intuition into an objective function. We said that each one of these values is a probability. So its maximal value is 1, right? So let's use just the complementary of the highest probability and define it as a loss. For lion, since it's generated, there is a patch in the image that is highly activated. So this loss will be very low. For crown, none of the patches are similar to crown, so the loss will be very high, okay? So this just translates our intuition directly into math. Now let's define the loss again, according to intuition, to be the maximal loss between all the nouns that we have. And we'll do a gradient descent step on ZT. Why on ZT? Wait just 1 second. But intuitively, what we want the model to do is be encouraged to attend to all the tokens, okay? Somewhere. Have some patch in the image, attend to one of the tokens. So why ZT? Recall that ZT is the noisy latent that was responsible for Q, for the queries, right? So when we shift ZT, we essentially shift the queries. When we shift the queries, we encourage the model, hey, put one query that is similar to the token that you neglected. Okay, this is why we do the gradient descent step on ZT. Okay, questions? No questions. Okay, so let's look at the process of attend and excite. So here we have our diffusion model, right? It takes a noisy latent and outputs a slightly less noisy latent. We understood that we should look at the cross-attention maps. Why? Because cross-attention is the place where text meets image. We found an intuitive indicator of when a token is generated and when it's not. And notice that we shifted ZT. So we need to repeat this diffusion step, right? Because now ZT is different. We changed it. So we need to repeat the process, need to repeat the diffusion step to get new cross-attention maps. And you can see here the result after attend and excite. Now, can anyone venture a guess on which denoising steps we need to actually apply attend and excite? Early ones, yeah, first ones, right?
Then once you have, for example, the crown attending some token, you probably continue attending grids.
Yeah, so we talked about diffusion models being coarse to fine models. So the first steps are the core steps. They are the important ones to determine the layout. Okay, so if I don't change the semantic information by this step, the layout is already determined. So if I start intervening in this point, it's too late, basically. The layout is already determined. So why is attend and excite so special? Now, we want to use these very noisy steps, right? These noisy steps, ZT is not a clean signal. If I wanted to use an external model like a VLM to ask it, does the image contain a cat and a dog? These signals are not clean signals that I can input into an external model. What attend and excite does is it enables us to get a clean signal from these very noisy steps that are critical to determine the layout.
הילה?
Yeah.
רק שאלה על הניתוח הלשוני, זה דורש ניתוח ידני שלה כדי להבין איזה שמות עצם חשובים ואיזה לא?
Yeah, so essentially you can use a part of speech tagger, which is considered kind of like a solved problem in...
אם כתוב תפוח שלא נראה כמו ארגז.
You can use a language model, for example, ChatGPT. So the ChatGPT can determine the target attention values for each one of the tokens. So for example, here we use 1, but if you want something to not appear, you can use 0. as your target attention value. So essentially, you can use a language model to kind of determine the target attention value for each one of the tokens in the text.
In the same direction, you focus on nouns, which makes sense, but sometimes verbs can be dominant in the interpretation of a sentence.
Yeah, that's a perfect question. And by the way, when we did this analysis on verbs, it looks like the same observation that we had for nouns does not hold for verbs. So it might be that the model encodes verb information in a different place in the network. But even when a verb appears, you will see that the attention values are low throughout the entire image. So this is basically based on the hypothesis that the attention values give us some indication as to this part of speech. So this holds for nouns, it holds for counting. I'll talk about, follow-up works in the next few slides, but it doesn't hold for verbs and it doesn't hold for spatial information, like spatial relations on top of, next to, and so on, which are more complex. And by the way, I think are probably not really encoded inside the model. So this kind of builds on the assumption that the model knows this information and encodes it somewhere in the network. Okay, so what's so special about attend and excite? Here you see the result before attend and excite, and here you see the result after attend and excite. Now notice that in our objective, we use the maximum, right? What this means is that the model can choose whichever patch it wants in the image to place that object. So it doesn't have to be a specific patch. This is what we call a non-restrictive loss or a non-rigid loss. This allows the model to completely change the layout of the entire image. So for example, here the model changed the location of the line to fit the crown. So let's see why it's so important. Let's take a look at results. So here we have our infamous cat and dog prompt. In about 50 to 60% of the cases, we'll get to cats instead of cat and the dog. And by the way, there is a localization bias. So if I had a dog and the cat, I would get 2 dogs instead of 2 cats. Okay? So you can see that after applying attend and excite, not only do we get both the cat and the dog, the layout is not restricted. We use the non-rigid loss, right? So the model can choose and pick the layout as it wants. So thanks to the non-restrictive loss, we have different layouts, different breeds of dogs and cats. But this is even more important when we look at complex prompts, such as this one, a playful kitten chasing a butterfly in a wildflower meadow. So before applying attend and excite, no butterfly is seen in the scene. Maybe this small artifact could be a butterfly. After applying attend and excite, not only do we get all the objects, which is kind of the obvious, right? But we do get also prompt alignment. And why is this important? We use this maximum, which is a non-restrictive loss. So basically, the model can kind of construct the scene in any way that it wants. Now we kind of rely on the model's prior. So the model does know what chasing means. And you see here that the cat is chasing the butterfly. So thanks to the non-restrictive loss, the model can kind of reconstruct the scene in a way that actually fits the prompt. So it's not only the existence of objects, it's also the prompt alignment that you get as effect. Question?
Yes. In the proportion of the butterfly in respect to the cat, it seems like a little bit unrealistic, right?
That could be like, this was Stable Diffusion 1.4. We have much more advanced models now. It might seem a bit unrealistic to some. As I said, the model struggles with spatial interactions. It's not perfect in that respect. We'll talk a bit about that and why that happens when we talk about video models, and I'll share some of my perspective on why reconstruction loss is really bad. But for now, I think it looks like it chases the butterfly in most of the cases. Okay, so let's do an analysis of what happened here. So we had Stable Diffusion who couldn't handle conjunctions and didn't have prompt alignment. After applying attend and excite, we can generate conjunctions. We have prompt alignment. We didn't do any training, right? And we didn't add any data. And again, the non-restrictive loss allows the model to reconstruct the scene based on the prompt. Any questions on attend and excite before I move on? Yeah.
How did you differentiate, like, because out the maximum loss? It's only for the specific pixel, and then like, can I include just the specific?
So maximum is a very useful function, right? In ReLU as well. It's like a function that you can use to derive gradients. It's a very natural operation to do. You just define the maximum over all the patches, and this is your loss, and you derive gradients based on that loss. And shift ZT based on the gradient that you calculated.
It's only the loss for the specific pixel, which is the maximum.
Not pixel, patch. It's in the
Okay.
latent space. Any other questions?
Wouldn't it be like better to do a sum loss or something, because then you can maybe do a gradient descent on all the intended tokens? One.
Someone what? So that could be also sensitive to the size of the object, right? So the sum will be larger if your object is larger and smaller if the object is smaller. So you need to be careful about defining an objective that is kind of uniform and not influenced by external things. So maximum is not is invariant to the number of tokens that you have, and sum is sensitive to the size of the object that you have. So you might need to do some more tweaks if you wanted to do sum. But I think the part about maximum that is really great is that it's non-restrictive. It allows the model to recreate the entire scene very naturally, by the way, since you do it in the first core steps, and then the model can use the next steps to refine the layout of the image. Okay, so again, due to the fact that we can guide models in very, very early generation steps, this is a very useful property, right? As I said, these are very noisy steps, and you cannot get a clean signal out of them unless you really try to dig into the internals of the model. So this is very useful for a wide variety of downstream tasks. This paper has like 520 citations in 2 years, and it's super useful for example, attribute binding. So this is a paper from Tel Aviv University. We can enforce that the model makes the hedgehog pink and the owl nerdy and so on and so forth. So this property of being able to guide models is super useful. But by the time that we hit 2025, this field of image generation became pretty saturated. So we're now able to generate pretty striking images, and most of the issues that we had before are mostly fixed. Okay, we'll talk about it at the end of the talk. But the question is, what's the big next challenge for computer vision that is unsolved? Now, I think a natural answer is video, because what video does is it takes that spatial information that we have in an image and it adds a temporal dimension. Now, this temporal dimension is a super complex dimension that gives existing architectures a lot of trouble. We'll talk about it a bit later. But this slide kind of shows you the best and the latest that we can do in video generation. 4 of these images or these videos, sorry, are actually from my paper, VideoGen, that we'll talk about at the end of this talk, which was recently accepted to ICML as an oral paper. And also, this presentation was created before VO3, but I just wanted to show you kind of what we can do now with video models. So VO3 is a new model from Google DeepMind that is able to generate both video and audio. So let's see this part that's called prompt theory.
A girl told me we're made of prompts. Like, seriously, dude, you're saying the only thing standing between me and $1 billion is some random text?
Honestly, the biggest red flag is when the guy believes in the prompt theory. Like, really? We came from prompts? Wake up, man.
I know for a fact we're made of prompts. Deny it all you want. The signs are everywhere.
You know how I know we're made of prompts? Because nothing makes sense anymore. We used to have 7 fingers per hand. I remember it clearly. Now we just have 5 fingers per hand.
So this entire video was created by VO3, audio and video jointly, just to show you how far this field of video generation has come in the last few years. Still, video is a very challenging task. I'll talk about the path that we did to get to VO3 and also why video generation is challenging. But just to show you an example of what we can do today. Okay, so why is video generation so hard? Assuming that we fixed image generation, why should video be exponentially more challenging? I'll give you 2 answers to that. The first answer is computational. We had stable diffusion before. It only had to generate a single frame, right? And already this model was very heavy. It was billions of parameters. Now we want to generate not just a single frame, but multiple frames for an actual video, right? We also need temporal layers to kind of connect between those frames. Otherwise, information will not be consistent in the temporal axis. So this already is computationally a challenge, okay? Now, the second one is the nature of this added axis. We all know that cursive dimensionality is real, right? So we added another dimension, but it's not just any dimension, it's a temporal dimension. So now our model, the same models that only see RGB information, it needs to learn not only appearance, but also motion, physics, cause and effect. Just to show you that motion is not a trivial task. This is a paper, again, from Tel Aviv University, doing motion generation on top of a human skeleton. So here we have all the joints in the body, and the model only needs to learn to move those joints. But it needs to learn that the feet need to touch the ground, right? What jumping looks like, you cannot jump in the air several times. So this is a very challenging task, especially when you want the model to learn it only from RGB pixels, which is the information that we have, okay? So the first paper that I'm going to talk about is called Lumiere. I did it in collaboration with Google, and it tackles the first challenge that we talked about, the computational challenge. So again, we're not in 2025 yet. Around 2022, companies started to get interested in video generation, obviously, right? So Google, Meta, and NVIDIA all had video models. Imagine Video from the team of Jonathan Ho, which is a very, famous and well-funded team. Meta had Make a Video, and NVIDIA had the linear latency, and all of them use the same solution to the computational issue. So what's this solution? We want to generate a video, say 80 frames of video, okay? And this is computationally expensive. So instead of generating all the 80 frames together, let's break the task down into 2 subtasks. The first subtask will be generating keyframes. So instead of generating the entire 80 frames, I generate every 10th frame. Okay, this is kind of like a storyboard of the video that I'm going to create. So this is the first model. Now what the second model does is it completes information within the windows that we have here. So this is called temporal super resolution. It completes the first 10 frames. It moves on to the next 10 frames, completes them as well, until it completes the entire temporal duration of the video, okay? On the surface, it looks like a great solution. Why? A, we reduce the computational cost very significantly, right? Each model only needs to process 10 frames maximum. And B, we are able to increase the model size very significantly this way, because we have our base model that generates the keyframes, and then we have 3 other temporal super resolution models that increase the temporal duration of the video. So we're able to kind of squeeze more parameters into the problem. And we said that scaling is a major enabler in deep learning, right? So on the surface, it looks like we benefit from all worlds. We solve the computational problem, we add more parameters to the problem. By the way, this is Imagine Video again from Jonathan Ho, and this model has 8.71 temporal parameters overall, okay? So what's the problem with this approach? The problem with this approach is what we call temporal aliasing. What happens is that we generate frames that are very distant from each other temporally. So the first frame might feature a person standing here, while the next frame features a person standing all the way there. So the model needs to complete here non-trivial information, the temporal super resolution model, right? You can think about the classic example of the fan. If we see the fan's wings in 2 time steps that are very remote from each other, does the fan turn right? Does it turn left? We don't know. This is what we call aliasing, information that is missing. Now, since there is so much information that is missing in the temporal dimension, the temporal super resolution model struggles to complete this information consistently across the frames. Now, think about also the fact that it operates in non-overlapping windows. So when it operates on the second window, it doesn't know what it did in the previous window. This creates this jitter effect that we see here. By the way, this jitter effect is common in all videos generated by Imagine Video. This was taken from their official website, okay? So what works in the spatial dimension very well doesn't work in the temporal dimension. So our solution will be no more temporal cascading, okay? No more cascades of models, different models that generate the temporal duration of the video. But we still need to kind of eliminate the computational cost, right? So how do we do that? On the left here, you can see the original architecture used by all these models that we talked about before. And on the right, you can see our proposed architecture in Lumiere. So let's break it down. You see here a diffusion model, right? It takes a noisy latent and outputs a slightly less noisy latent, as we talked about at the tendon side. Now, this network is what we call a unit. It downsamples the information, There's a middle layer that keeps the resolution the same, and then it upsamples the information back. So you can see that here we have a dimensionality reduction in the spatial dimension. So the spatial dimensions of the frames are downsampled, but no downsampling in the temporal dimension. This is what makes these networks so costly. So what we propose to do at Lumiere is whenever you do spatial downsampling, also do temporal downsampling, which is learned by the model. Okay, so what we have here is kind of similar to the keyframe approach that we talked about, only here those keyframes are learned by the model. And there's no two separate models that do the completion of the temporal information. So we have this downsampling. Here we'll put most of the compute because this is kind of the compressed representation. And this is the efficient representation that we have. And the model must learn to reconstruct that information in the up branch. So when you compress something, you need to learn to decompress it back, okay? This is an approach that was used for understanding, but not for generation, again, because of that assumption that cascades work really well in the spatial dimension, and why not apply them to the temporal dimension and add a lot of more parameters? Any questions on this approach? So you can see here a direct comparison. We took the first frame from Imagine Video and generated the video with Lumiere. You can see how much smoother those videos are temporally. And if we compare, we had 8.71 billion parameters in Imagine Video, only 4 billion parameters in Lumiere. So we reduced more than half of the size of the model. Here we had to generate the video with 4 models. We had a base model and 3 temporal super resolution. Here we have 1 model, a single model that generates the entire temporal duration. And we were actually able to significantly improve the videos that we get. So bigger isn't always better. It depends on the modality that we're using. And the temporal modality is very, very different than the spatial modality. So we need to do it with kind of an understanding of what temporal information actually means. So here are some results with Lumiere. Again, compared to VO3, it might look a bit underwhelming, but remember that this was 2023, and the best that we had are those G3 videos. So Lumiere was basically maybe the first model to show smooth motion, smooth spatial information, videos that actually look like real videos. So this got us a lot of attention from the media, technology outlets such as The Verge and ZDNet. If you like Yannick Kilcher as much as I do, you're welcome to watch the video. And very much to the pleasure of my mother and my grandmother, who finally could understand what I'm doing and why it's so important. Articles at Ynet and in the kind of conventional media. So Lumiere got a lot of attention. Okay, any questions on Lumiere before we move on? Yeah.
This time you added the model to the model, and you said at the beginning that you didn't use any data for training, but in this time you changed part of the model, so you did.
We did train the model on the same data that the previous model was trained on.
The same data.
So here we reduce the size of the model, but obviously you need to have millions and millions of videos to train video models. Okay, so what are some of the use cases that we can do once we have a video model that is trained? So one of the best use cases in image generation, which is again very much explored by researchers here at Tel Aviv University, is what we call customization. I'm able to feed the model a few examples of my dog or my favorite style and have the model generate several images of my dog in different scenarios or my favorite style. So another thing you should know about the models that came out in 2023 and 2024 is that they are mostly inflated models. So we talked about the spatial layers and the temporal layers that we added. Inflated models freeze the spatial layers and take them from an existing image model and only train those added temporal layers. Okay, why? Because image generation is kind of 25% of the solution towards video generation, okay? So once you have an inflated model, a naive approach to do customization is say, okay, we know how to customize an image model. Let's customize the base image model and inject those weights into the video model, right? So it turns out what happens when you inject spatial customized layers, you get very artifacty results. Now, why does this happen? We have those injected customized layers, those yellow layers that we're seeing here. Now take into account that those temporal layers are used to a certain distribution from the spatial layers. When I shifted the weights of the spatial layers, the output shifted its distribution, right? So those temporal layers get out of distribution information, which then output out of distribution information, and so on, which gives us those nasty artifacts. Now I have a paper called Still Moving. We won't have the time to get into the details very much, unfortunately. But in a very high level, what we do in Still Moving is we're able to turn this video model into a dual mode model. So this dual mode model can function as both an image model and a video model. And importantly, when it functions as an image model, it still passes through all the layers, including the temporal layers. So then we can fine-tune the model on the image state with the temporal layers, okay? This ensures that this is not out of distribution because the temporal layers know the image information. And then switch the motion switch on and turn it into a video model and see how the model adds temporal information into that spatial pair that we have, okay? So again, I don't have the privilege to get into the details, but I will show you some results. So we are able to take a few images, still images of this plasticine cat, and fine-tune the model on these images. And then once we switch the motion switch on, the model adds motion to the scene. To me, the most exciting use case is actually stylization. Because here I only gave the model the still image with the splash in the background. And personally, I expected the model to create kind of in distribution motion, right? Maybe the woman will move a bit, maybe she'll raise her hand or something like that. But it turns out the model is able to customize also the motion based on the reference image. So what happens is we shifted the spatial weights. And as we said, the temporal distribution, output distribution shifts with the spatial distribution. And it turns out that the model can use its prior to understand that the splashes in the background should manifest as splashes of color in the video. Now, this is consistent across styles. If I give a reference style of vector art, I'll see motion that is customized to vector art. So things popping out, things created. So again, I only gave the model a still image, but it is able to use its temporal prior to match this image with a corresponding motion time. If I have drops, I'll see the same drops kind of dropping and spilling from my videos. And this is what I think is one of the most beautiful things about video models. We might want disentanglement between spatial information and temporal information, but entanglement is actually a beautiful thing. Once temporal and spatial are entangled, when we shift the spatial, the temporal shifts with it and can be customized with it. Okay, so this is still moving. And the final work that I'm going to talk about is VideoGen. So far we talked about how amazing video models are. We can customize them. Amazing temporal customization with spatial customization. But the truth is that video models still struggle very much with understanding this temporal dimension. So they struggle with motion, they struggle with physics, and this still goes on. This is, by the way, the state-of-the-art model by Meta. It's called MovieGen. And you can see that it struggles so significantly with very basic understanding of the temporal dimension. Now, to me, the most problematic example out of these three is actually the man walking in a straight line. Why? We can make the claim that the model didn't see a lot of cartwheels or didn't see a lot of pull-ups, but walking is basically one of the most simple types of motion that we can think about. The model saw millions and millions of examples of people walking in its data set. Okay, this model specifically was trained on 100 million videos and 1 billion images. So why does the model struggle so much with motion that seems so simple and it saw so many times in the training set? Now think about the loss that we're using to train these models, which is a reconstruction loss. What a reconstruction loss does is we have this ground truth image and the predicted image, and we basically compare them pixel by pixel with an MSC loss, okay? So it essentially compares each pixel to each pixel. Now think about this man who's switching legs in the middle of the video, okay? When we talk about reconstruction-wise, when the legs switch, almost nothing changes in terms of RGB pixels. So of course, the model does not know to distinguish between a coherent motion and incoherent motion. It's because its loss does not encourage temporal information to be learned. Okay, so you might ask yourselves, what happened with VO3? It looks super amazing. So I don't have access to VO3, but I was able to find a few videos to show you kind of that this problem still holds for VO3. I muted this video because the woman is pretty angry. So she breaks the glass and then the glass magically reappears. And in this video, someone tagged me in it on Twitter. This person is very upset with his computer. It explodes, but then the screen stays intact. So this just goes to show you that even DeepMind, who trained this model probably on all YouTube videos, okay, is not able to still overcome this limitation. This limitation is real and it's profound. So let's understand if our intuition is correct. Okay, we said that the loss is problematic. So what we did is a motivational experiment. Let's take these regular videos and randomly shuffle the frames. So the appearance here and here is very similar, right? But we can obviously see that this is incoherent and this is coherent. And let's try to kind of recreate the training process of the model. We said that the model noises both of these signals, right? And then does this reconstruction loss. So let's measure the loss for the coherent video versus the incoherent video. These are the two orange lines that you're seeing here. The straight line is the original model without modification, and the dashed line is after we randomly permuted the frames. You can see that the objective is almost invariant to this information, so the loss does not distinguish between the shuffled video and the original video. So I did a very, very kind of abrupt temporal interruption here, right? I shuffled the frames, and still the model is not able to distinguish between these two videos, which kind of shows us that this objective is indeed kind of invariant to temporal information. Any questions on this? Okay. So what should we do to solve this? Let's teach the model an explicit motion prior. Basically, let's change the objective of the model. But the language that the model understands is RGB, right? This is what it understands. It understands reconstruction. So how can we use RGB information to encode temporal information? What we do is we use a representation called optical flow. Optical flow computes what we call a dense displacement field between pairs of frames. So what does that mean? It means that for each pixel, we compute a vector that points to the direction that the pixel moves in. So if I move from here to here, there will be a vector pointing in the direction where I moved, right, between the two frames. Now, this is a vector, but I need to translate this into RGB information. So each vector has two properties, an angle and a magnitude, right, a length. So each angle will be mapped to a color, such that each vector is represented by a different color, okay? And then the luminance of the pixel will be determined by the magnitude. So if I move a lot, the pixel will be very intense. If I don't move, the pixel will be white. So let's see what it looks like. This is an example of our training process. Here you have the original RGB video. And here, whoa. And here you have the optical flow representation. You can see that each of these colors represents not an RGB value, but a direction that the leg moves in, okay? And we can see that this leg moves a lot, while this hand, for example, doesn't move almost because of the luminance of the pixel, okay? So we now encoded motion in a way that the model actually understands. Now let's think about the case where the person switched its legs, right? So in terms of RGB, we said there's almost no, but but when we look at the optical flow, instead of being, for example, green, red, green, red, green, red, we'll see an abrupt color in the middle, right? Because the leg will move in an unorthodox direction, okay? So what was kind of undetectable in this RGB space is very detectable in this optical flow space. Is that clear? Mm-hmm. Okay. So the way that we construct VideoJam is by adding two linear layers. That's it, only two linear layers. The first one is in the entrance to the model. So we have a linear layer, this linear layer, that kind of converts our noisy video into a latent representation. We'll just extend this linear layer with additional rows. So now this additional matrix combines linearly this appearance signal with this motion signal. And I will have a latent representation that is a linear combination between the representation of the appearance and the representation of the motion. Okay? So this is the latent representation that the model works with. Basically, this is the diffusion model. This is the heart of the model. This layer that we saw here is just kind of the entry to the model. So we don't touch the actual architecture of the model. We don't add any parameters. We don't add any layers. This stays the same. But in the output, we project the internal representation to the appearance. And then we add another branch, which projects the internal representation into motion as well. So the model now needs to learn a dual prediction. It needs to learn to predict both the appearance and the motion from this single learned latent representation. Okay? One other thing is that even though we don't change this architecture, we do need to train all the parameters of the model. Why? We know that the model does not understand motion. We now add this additional signal that it needs to predict. So we must train the model so that it knows to understand this new dimensionality that we're teaching it, right? So only 2 added linear layers, but we do train the entire model. Questions on this? Yeah.
So you need to add to each frame like another representation of the motion?
Basically, yeah, you need to calculate this optical flow. I will say that this is considered kind of an almost solved problem in computer vision, calculating optical flow. So there's a network that takes this video and processes and outputs the optical flow for this calculation.
I mean, but like a computational wise, how do you have like a superpower resources of Google to do it?
This is done at Meta. This is not a university paper. Okay. We had to retrain the model. I will show soon that it wasn't done on the entire data set, but we did have to retrain the model. I will take other questions at the end just to make sure that we get to everything. So let's put it into mathematical terms. And I promise you, this math will be useful in 2 slides, so no need to worry. So M is our diffusion model here, and it takes 2 inputs. It takes the noisy video, and it takes the noisy optical flow, XT and DT. And then we have this linear matrix that transforms XT and DT to the single learned representation. Y is the text prompt, and T is our time step in the diffusion process, right? Gradually denoising information. Now, W out is the linear projections that predict the appearance and the motion. And the loss is just the original loss of the model, only now it needs to predict both appearance and motion, and not just appearance. Okay? So why did I tell you all of this? At inference time, theoretically, we don't need this motion signal. We can just get rid of it, right? We just need the actual appearance, the actual video. So how can we use this motion signal during inference to improve the model and make sure that it creates a video that is temporally plausible? So what we do is called guidance, okay? Like classifier-free guidance. This is basically the probability that the model was trained to maximize. The model is trained to maximize the probability of the video and the motion given the text, okay? This is what we did during training. So let's not sample from this distribution, but from a slightly modified distribution. The first term of our distribution will be just this, the original sampling distribution. The second term is what we call classifier-free guidance, where we aim to maximize the probability of the text given the video and the motion. Now, classifier-free guidance is something that we always do in every diffusion model, so this is not new. The new part is this term here, which aims to maximize the probability of the motion representation, DT, based on the video representation and the text. Now notice that this DT is predicted by the model. So it's a noisy motion representation. Unlike this term here and this term here, now the model kind of guides itself. So we use the previous motion representation or the predicted motion representation to guide the model in the next step based on a noisy signal. It's not obvious that it's going to work, right? It turns out that it does. And this actually allows the model to guide itself during the generation with its own prediction, which is kind of a cool concept. Any questions on this? Yeah.
Shouldn't it be enough to guide the outputs on the motion? Like, why do you need the other term?
Guide the output?
You guide it on DT, which is the motion,
Yeah,
in the middle term, so
yeah.
shouldn't it
Oh,
be
here. No, it's not guided. It's predicted by the model. The model takes xt dt and predicts
the-
xt minus 1 and dt minus 1.
here by ansatz?
Here, okay, look at this as a probability, right? What's the probability that I'm trying to maximize here? The probability of the text given the video and the motion. Here, I try to maximize the probability of the motion. And this term is aimed to kind of improve the temporal coherence of the video because we want to maximize the probability of the motion. Okay, so we do this practically just like they do it in classifier free guidance. We train the model once to predict both video and motion, once without the text and once without the motion. And we kind of do an extrapolation. We take the prediction with all the terms and distance it from the prediction without the text and from the prediction without the motion. So let's take a look at some results of VideoJam. On the left here is the state-of-the-art movie gen model by Meta. And on the right is after we apply VideoJam. You can see how much our model improves the temporal coherence, the motion understanding, the physics understanding very significantly. It also improves drastically the temporal coherence and motion understanding in comparison to state-of-the-art models like OpenAI Sora. So this is a model that OpenAI invested millions and even billions of dollars training, and we were able to improve it with a simple intern project, right? With not a lot of resources. I'll talk about it in a second. Another example is Kling. Again, a company invested a lot of resources in training this model. And we were able to improve it by understanding why video models kind of fail to understand temporal information. So a few examples here of what this model can do. Complex motions, water motions, kind of motion types that existing video models struggle with significantly. And if again we do this breakdown of what happened before VideoJam and after VideoJam, we can see that the original model was trained on 100 million samples. We only trained our model or fine-tuned the model on 3 million samples, so less than 3% of the training data of the model. So significantly reducing the number of videos that we show the model. We only added 2 additional linear layers, so we didn't increase the scale of the model. And it resulted in a significant boost in motion, 72.7% preference to VideoJam over the original model. And again, this just stems from our understanding of why the model fails to understand motion and physics. Okay, so again, VideoJam was covered pretty extensively by the media. This is actually a 2-minute paper video that I really recommend if you like to kind of understand water motion. It talks about how complex it is to model water motion and how VideoJam actually nails this part. And let's talk a bit about future works and what diffusion models still don't understand. So we talked a lot about image models and what they do understand, but there's still a lot that they do not understand. For example, spatial interactions. If I ask for a pink square on top of a green circle, the model struggles with that very significantly. Now, this can be mapped intuitively to the same reason that we had here with this reconstruction loss, which is kind of biased towards appearance, bless you, and compromises other information such as spatial interactions and such. Another example is a woman doing yoga. You can see that the model really struggles when it comes to complex body poses. Biases is another great thing. Like when I prepare this talk, I asked a diffusion model to generate an image of a professor to give me an inspiration, kind of what should I wear for this talk. But unfortunately, none of the images looked like me. They were all of men, all with beards, all with glasses, all at libraries. We do not know exactly why this happens in diffusion models. We talked about motion a lot, but physics is still an unsolved issue. And why is that? Optical flow is not really a physics representation. You can think about the example that we saw of the woman moving through the pole, right? Now the pole is static. In optical flow, you'll see just white pixels. And you'll basically see the woman moving backwards and forwards. So it looks like it's coherent and the optical flow does not really capture physics information. So there's a lot of attempts to kind of fine-tune video models on physical representations. This one actually created a data set of physical simulations and tried to just fine-tune a video model on these simulations. They found results that are very much in correlation with what we did. So the model optimizes basically the colors, the shapes, but not actually the physical correlations or transactions between the objects. Another really interesting thing to work on is long video generation. So as I said, computational restrictions are still very much real. So even Veo can only generate maximum of 10 seconds of videos, I think. But then if we want to create an actual story of this car moving through different scenarios, right? You'll see that this approach kind of does it, but it doesn't look realistic, right? So the transitions between the frames are not smooth, they're not as we would expect, right? So we're still struggling with getting video models to actually create stories. And these are just a few directions that we can work on in the future. But that's it for me. Thank you so much for listening. And if anyone has any questions, you're welcome to come and ask them.